What's your minimum specification?
Hi everyone, and welcome to another of Ian's interviews. Today I have a very special guest about a topic so very close to my heart. You've seen me do videos about calculating numbers of digits of pi before. Now, I'll be honest, that only scratches the surface to how much I've researched this thing. This is a record I so dearly want to put on my CV, on my record of accomplishments before I die. However, the record's just been broken again, and for Emma Haruka Iwao, it's the second time she's broken the record, so I've invited her onto the channel to showcase exactly what this record means to her, to Google Cloud, her employer, and the wider scientific industry. So please please join me in welcoming Emma to the channel. Hi, Emma.
Hi, thank you so much for having me today.
So this is your second record. I've put up here that you've calculated 100 trillion digits of pi. And your previous record in 2019 was 31.4 trillion digits of pi. So 10 trillion times pi digits. But this is your second record. Is the second one just as sweet as the first?
Yes, definitely. I'm so happy I was able to do this twice, so that people will know the first time was not a coincidence. We can do this reliably.
So that means there'll be a third time and a fourth time, and I'm just going to have to wait and wait and wait to get the record myself. Is that what you're saying?
Well, I'm not sure. I think there are a lot more people working on pi calculations like you. It might not be necessarily me, but I'm certainly interested in trying this again.
I asked a few of my audience for questions for you, just to see if they aligned with mine before we chatted. And I think the most frequent one that came up is why. Why would somebody calculate so many digits of pi?
Yeah, there are many reasons, and I think so because this is a tech channel. I'd say pi is a very very good benchmark to measure performance on computers in long term. So we use the same mathematical constant from well before the birth of electronic computers. We use pi with manual computers. We use pi with human computers, like people who calculate pi by hand. And now we use electronic computers. And there are a lot of benchmarks, like you can name it, but many of them are used for maybe a decade, maybe a few decades. But pi is something you can compare the performance between the 1940s, 2000s, 2020s, etc. So I think it really shows us how much we've achieved. And obviously, we use different algorithms. They have different complexities, and we have different architectures, everything. But overall, combined, I think this really shows how much progress we are making.
This benchmark, I mean, members of my audience will know it's Y Cruncher, Alex Yee, the guy behind it. We both know him. It's not necessarily a test of computational ability, is it? It relies on so much of the system around it.
Yes. For world record class calculation, it's more about storage and I/O and memory. For smaller calculations, like so, Y Cruncher can calculate millions, billions, and trillion decimals of pi, all in memory. And in that case, it becomes more like computing power and memory bandwidth. And for anything bigger than the main memory, like a few terabytes, then it suddenly becomes a heavy I/O benchmark program.
So, in terms of street cred, I guess I should ask, how many digits of pi can you recite personally?
I can recite 3.14159. Is it? A few digits.
I think that's enough. I mean, that's enough for most calculations. I love it when we see media such as your record, such as Timothy's record, Grisson's record, and now your record again, all saying, well, with 30 digits, you can do anything you want on Earth. With 80 digits, you can do everything you want in the universe. I would point out to people to go see Matt Parker's video on what is pi to the pi to the pi to the pi. That's a perfect example of kind of why so many digits of pi would be needed. He cites you, and you've even had an interview with him recently about this record.
To brute force the problem, I think the other way to prove it is mathematically, like create a proof, and another like the other way is always. So I think in math and computers, there are certain ways you can do with computers and with a lot of data, and there are certain ways mathematicians and other theory crafters can do with pure theory without much data. And I think this particular question lies an interesting spot between these two.
It requires a few smarts rather than just brute force. So with you taking these records, I think there's a kind of subtle irony here because you've actually studied under somebody else who had the record themselves, haven't you?
Yes. So I went to a university called the University of Tsukuba in Japan, and I studied computer architecture and joined a lab. And one of the professors there was Professor Daisuke Takahashi, who did a world record. I think he has like quite a few world records of calculation of pi using supercomputers.
So he knows you have the record now. Have you been in touch with him since?
Yes, I wrote to him last time and this time as well. He said congratulations, and I think I met I met him at SC after the
It's
first world
supercomputing.
supercomputing in the US.
So as this is a hardware channel, with your record, I'm going to ask you to go through the hardware you used. I mean, it's very easy that someone might think that, hey, you need a modern day supercomputer to break these records. But the reality is it's kind of been a single computer type solution based on the software used for quite a while. But in your unique case, you're using cloud resources.
Yes. So the last Pi world record with a supercomputer, like any parallel computer, was in 2009, and since then all the records were done by a single node computer. And the I think the tricky question is how. So in order to calculate pi, you need to move a lot of data, and moving a lot of data is quite difficult even on a supercomputer. So let's talk about it later. But for the architecture, we use one virtual machine for the main calculation. This is a what we call N2 Hymen 128 machine type. It has 128 vCPUs with the Intel Ice Lake processors, 864 gigabytes memory. And in order to calculate 120 digits, you need about 550 terabytes of storage. And the maximum amount of storage you can attach on Google Cloud is 257 terabytes. So we need to work around that limit. And one of the ways to work around the limit is using network attached storage. And we decided to use iSCSI, the network block storage protocol over TCP. And there were 32 storage nodes as iSCSI targets, each running two iSCSI targets. And in total, we had 663 terabytes of SSD disk space attached with iSCSI. And everything is running in a single Google Cloud zone connected with 100 gigabits per second Ethernet. So you can communicate with pretty much 70, 80 gigabits per second effective throughput. So it was pretty fast. And for the final results, we had additional 100 terabytes of SSD directly attached to the main compute node.
I should point out the reason that you've used Google's cloud resources is because you're a Google Cloud developer advocate.
Right, exactly.
So your goal here is also to promote the use of Google Cloud services for this type of operation.
So this is more about my personal interest and dream. So at Google Cloud, so the team name is Developer Relations, and we create demos, experiments, and run use Google Cloud for many different purposes. And we often individually come up with some ideas of using Google Cloud to showcase some of the capabilities and what you can do with the cloud platform. So I wanted to calculate pi for a long, long time, like here. I started using computer when I was 11 years old. Well, a personal computer, not a specific word processor or console game. And then one of the first programs I downloaded and ran was SuperPi, which is also
Yep.
developed by the same people, Professor Takahashi and
Wow.
gosh,
I
I
didn't know
don't.
that. I've used that a lot. I didn't know that. Okay. That's interesting.
Yes,
That brings a big circle round. Okay.
and SuperPi was able to calculate up to 16 million digits of pi. But the computer only has 16 megabytes of DRAM, so it wasn't enough for 16 million digits. I think I did 1 million digits, probably most. And then the program had a text file in the same archive uh, explaining what their world record is. And the world record back then in the 1990s was 60 billion digits. And that's how much
Yeah.
a supercomputer can do. And the personal computer back then running Windows 95 was able to achieve. And I was like, okay, so you can calculate more digits if you have faster computers. And I want faster computers, but I don't have a supercomputer. What can I do? And then, but so I sort of wanted to calculate pi, but I had no idea because I wasn't particularly good at math and algorithms. And then after joining Google Cloud, well, in 2009, the first world records with a single node machine came out. Like actually two. So the first one is the one by um, Ferris Bellard, he did it individually, and the second one is using Y Cruncher. And Y Cruncher is actually something you can download on the internet, and many people use it for benchmarking. And so I knew how to use it. And after joining the developer relations team, I was like, we we maybe can do it. We have computers that are fast enough. We have a lot of storage, and that was when we are planning for Pi Day 2019. We as a team we have a tradition of celebrating Pi Day, and we have used Y Cruncher on a single node machine on everything on memory. But for 2019, I ran some numbers. We had enough bandwidth. We had enough storage. The processors are fast enough. Um, I think we can do it in 5-6 months to calculate 31.2 trillion. So
Yeah.
that's how we came up with the idea. And my managers and everyone around me supported the idea. They were not quite sure whether we could actually break the world record, but we did in the end.
It's. I remember reading that record, and that's when you first flew onto my radar. Because at that time, I'd already been speaking to Alex Yee, the guy who created Y Cruncher. And I was like, surely there are faster ways to do it. Sure, I was looking through, what nodes you were using, the storage, the network bandwidth, and I noticed that you were being very network bandwidth heavy rather than DRAM heavy, just because that's the utilization of the Google Cloud platform you were using. But I do have to ask, because this is a trouble I've had, is how did you get somebody to sign off on it?
So developer relations and Google Cloud is kind of interesting place when you have an idea, and if you can prove it using Google Cloud, there is a way to make it happen for many experiments. And my director back then, Greg Wilson, is also a Pi enthusiast. So
Mm.
he really worked to support the proposal.
I think I remember calculating back with your 2019 records that to use the Google Cloud resources at standard industry rates at the time, you were looking at somewhere around 6 figures US. Do you have an
Yes.
equivalent number for this new record?
So there is a GCP, Google Cloud calculator for pricing, and you can put all the configurations there and calculate the numbers. It's somewhere between 300K, 500K. There are some cost saving techniques we
Mm.
used since for this calculation, but for the actual list price, it's still 6 figures. So that's um, cheaper than a typical supercomputer, I think. Could be more expensive than actually. So the 50 trillion digit calculation is something you run in a house with used hardware resources. So you can buy on eBay. That's something you can go really, really cost effective. Cloud is not that cost effective, obviously, as cheap as using used hardware. So it's in the middle.
It's I think if you told somebody that you were able to do this calculation for that amount of money rather than build a massive supercomputer, you know, the industry is talking about exaflop scale, and we can just run this on what is effectively 32, 33 nodes on the cloud is quite impressive. Though I think one of the scalers for me is your first record took 121 days, and this new record is 3 times the size, but you only increase the time by 25%. Is aside from hardware improvements, is there anything special you're able to attribute to not having that linear scaling?
I think it's almost exclusive of the hardware. We use similar optimizations. We added some new techniques like assigning Y crunchers, IO threads to the particular NUMA node, which has the NIC, or trying out different PCI Express, different IO schedulers, and TCP congestion control algorithms, etc. One big difference is we switched the main compute node from Windows to Linux, and the reason is Windows Windows the I2G implementation of Windows doesn't really use multi-cores effectively. So there is a hard bandwidth limit around 20, 25 gigabits per second. And we obviously wanted to achieve faster. And then I tried Linux as well. And Linux seemed to work much better in this particular area. So that's the reason we switched from Windows to Linux. The reason we used Windows uh, for the first calculation is Y-Cruncher's documentation said it's more optimized for Windows. So
Yep.
I,
Yep.
I thought, okay, this probably works out. It fills the 16 gigabits per second bandwidth we had at that time. So I thought it was a better choice. And this time the bandwidth was increased from 16 gigabits per second to 100 gigabits per second. So Windows wasn't able to handle that. So we switched to Linux.
Were, were you actually able to extract 100 gigabits per second read and write?
Um, so there are some overheads like TCP headers.
Yep.
The benchmark we did was around. I can pull up the numbers. I have a spreadsheet of all the numbers.
I would fully expect you to have many spreadsheets on this because it sounds like you've gone through a lot of loops profiling the workloads just to make sure you've got the right sets of configurations. I think you've even given some of this code out on GitHub so people can do their own testing, haven't you?
Right. So we have Terraform scripts, shell scripts, and everything published on GitHub. It's linked from one of the blog articles we have. So please check it out if you want to actually look at it. So the bandwidth, this is the number you can get from Y-Cruncher, not necessarily the actual network throughput, but it's about 11 gigabytes per second, gigabytes per second. So if you convert it to
Yeah,
gigabits per second,
88.
yeah,
Yeah.
88.
So one of the other questions I got from my audience who aren't so well versed with this sort of calculation is that they asked, can you take the result from your first world record and use that as a starting point for your second world record? Now, the answer is obviously no, but I'd love for you to explain why.
Sure. So the biggest, simplest reason is Y-Cruncher doesn't support it. We use Y-Cruncher. And there are
Get
a
on it, Alex.
lot more reasons. The intermediate express state storage is much bigger than the final product. You obviously need to store multiple variables to calculate pi, and when you combine everything, you get the end result. And you need to save all the precision to restart from there. So you don't just store like 20, 30 terabytes of data. You need to store hundreds of terabytes of data to restart from there. So it's actually technically more difficult than simply starting from the digital pi that someone did in the past. And the third reason, I think this is probably the biggest. This is a benchmark program, and this is sort of a competition like sports. And we obviously want to do and measure the performance from start to end. And so I think this is why a lot of programs out there don't support restarting from past records, past checkpoints with different configurations. And the idea is measure the performance, reliability, and progress in computers. So I think all of the world records in the past calculate from start to end. So um, summarizing technical reasons, Y-Cruncher doesn't support it. Restarting from past calculations is more complex than simply taking the digits and running the program on top of that. And thirdly, this is competition benchmarking, and you probably want to do it from start to end.
It's a good thing you brought up reliability, because I remember with your previous record, part of the messaging that came out of that was to do with Google's use of live migration to mitigate errors that could happen at any point in those VMs. Not so much of the messaging this time around. However, in Google's blog, you did say over 80 petabytes of data was read or written with no bit errors at all. That's quite impressive. Is there anything to add onto the Google Cloud between previous record and this record?
I think I'm not sure what has changed for the cloud platform itself. The biggest change. So this is again some software configuration change. We turned on the CRC integrity checking for Iskaji. So last time I checked the configuration before starting this this calculation, and I didn't use it. I thought I had the CRC checking on, but it was actually off. So
Oops.
I think that is why we had some core efficiency too large errors with Y-Cruncher last time. And this time, because we had the integrity checking, we didn't have any I/O errors whatsoever. And live migration happens regardless whether you have any hardware problems or not. We do live migrations when we apply upgrades to underlying VMM and operating systems. We do live migrations for other maintenance reasons. So it's not necessarily tied to any hardware errors. That happens. You get notifications when live migrations happen. Live migration didn't interrupt the calculation. So I think that also proves even if you have a lot of DRAM memory access workload, you can still rely on live migrations.
Well, obviously, when I run this software at home, I just have the base interface that tells me how well the compute is going. There are elements of a Google Cloud that helps you monitor a bit more effectively this sort of large calculation over multiple nodes. And be honest, how often were you checking to see it was still running perfectly?
Probably once a week, maybe twice, once every few weeks. So I set up. So one of my teammates was Google monitoring and logging expert, and he set up a dashboard to monitor all the I/O and CPU usage. And we also had alerts set up for monitoring. And So one is when you don't have the Y cruncher process. So if the process count is 0, you get an email. And the other one is when the CPU usage is less than 1% for like 1 hour, which is likely the program has stopped.
Yeah.
So you get an email. So as long as you don't get these emails, you know that calculation is still going on. So you don't actually need to open the console and check it frequently. You can still see it's running. That's cool, and I really enjoy like watching the console. But that's probably just me. And also we set up logging to extract the ycruncher checkpoint file, which has some progress and indications, so you can monitor that from the logging system instead of actually logging into the into the compute node. So that's how we monitor the system.
It's interesting that you bring up CPU utilization because my next question that I've got down here is the fact that during this whole compute, I noticed on your output file you only had a 17% CPU utilization, which means that the bottleneck is elsewhere.
Right.
Where is the biggest bottleneck moving forward for this sort of thing?
It's storage, or in a bigger computer architecture sense, it's memory. So secondary storage is essentially the secondary memory, and the primary memory is DRAM. And for this is not specific to Y cruncher or Pi calculations, but we don't have enough bandwidth to feed the CPU for continuous data flow. Disks are obviously much slower. We had 100 gigabits per second Ethernet, but even if you had NVMe SSD directly attached to CPU, it's still slower than the processors. Even the DRAM is still slower. So we are the biggest bottleneck for any calculations, any workloads, or most workloads, is actually the main memory and the storage. So that's the challenge. And the CPU utilization actually increased from the last calculation. I think we had a lower number for the last calculation, and the network bandwidth increased by 6-folds, but CPU performance didn't increase by 6-folds between 2019 and 2022. So the CPU utilization value actually got better slightly.
You say that essentially what is memory storage being a limiting factor, but you also only used a Google Cloud compute node with only 860 gigabytes of memory. I mean, we were talking before this started. I'm actually sitting in front of a system with 2 terabytes of memory, and Intel's current high-end stuff, you can do 24 terabytes of Optane across 4 sockets. So why did you end up using such a small amount of memory on your compute node?
And I think calling 864 gigabytes a small amount of memory is an interesting
Yeah.
take. But so the most important factor is the network, right? So and this is specific to Google or any cloud platforms. You have some set configurations for different machine types, whether you optimize for memory, CPU, storage, or whether you need a GPU or not. And you can't unfortunately maximize everything. There are levers for each parameter, and in order to get 100 gigabits per second network throughput, there are specific machine types we need to use for Google Cloud, and that one of them is N2, the N2 series. And the biggest machine you could get with the N2 machine series is 128 vCPUs and 664 gigabytes memory. There are other machine types that offer up to, I think, 12 terabytes of memory using some of the technologies.
Yeah.
They don't support the 100 gigabits per second Ethernet. So that is why we use the particular machine type.
There wouldn't be much value in GCP putting together just a special instance just for this project, because you wouldn't be selling it to anybody, I guess.
So as a developer advocate, my job is make sure that you all can use the same technology and the products. And it's not like using some secret technology to do something. My job and my team's job is to show what you can do with cloud or
Yeah.
technology or software, computer science, anything. So we often opt to use public offerings, open source products. And this time, Y Cruncher is not open source, but it's still something
Yeah.
more accessible. So that is how we often design architectures and run experiments.
Looking to the future with CPUs having more memory channels with things like HBM, CXL over the next 3-4 years. Those all sound like technologies that would be really good for this sort of task.
I think HBM has tend to have lower capacity,
Yeah.
and that could be a bottleneck for this kind of workloads. So if you can fit everything in the HBM memory size, then that's probably fine. And the Fugaku supercomputer uses HBM on ARM, and for specific workloads, that works better. And for Pi, if you can somehow attach 1 petabyte DRAM to a CPU, that's still not possible with any architecture. At least for x86 architecture, it's not possible yet. You can obviously calculate everything in memory. That's faster. So it's step by step. Currently, we use network. If you can directly attach everything to a single node using regular PCI Express lanes, obviously that's faster, and that's still within the scope of standard hardware. And if you can insert RAID cards and attach like fully utilize PCI Express lanes, usually modern CPUs have 48, 64 PCI Express Gen 4, Gen 5 lanes that can achieve hundreds of gigabytes per second of throughput. And so that's way slower than the main memory, but you can still achieve faster throughput. And somehow, if you can attach everything as DRAM, that's thousands of gigabytes per second. That's way harder, way faster. And if you can somehow increase the bandwidth of DRAM, maybe using HBM or some other kind of technology, maybe using much wider interface, then you can still increase the performance. But that's not quite as fast as the CPU itself. If you work for many workloads, if you fit something in the L1, L2 cache, then you can do it much faster. But they're usually in kilobytes or megabytes. So it's gradual increase, gradual change from hard drives, network, SSD, and then PCI Express. Then you have DRAM. So with everything, you don't just have this fastest single component somewhere. You need to take a good balance of all the factors.
It's I've been spending some time recently with companies dealing with composable infrastructure, so you end up having what is essentially a node being a full 42U rack. Put in as much memory as you like, put in as much storage as you like, and it all just becomes one big machine. I mean, talking to your point about just expanding PCIe, and beyond that CXL, it's going to be a very exciting next few years, I think. And you're going to have to wait. You're going to have to see what Google Cloud deploys, I think, for your next task.
I'm hope so. I don't have any specific things, but I'm really excited to see the difference between 2019 and 2022. We essentially use the same platform, but the platform got more than twice as fast, and it even when we are in the computer industry, semiconductor industry, it's really easy to forget or dismiss how faster computers get each year or over certain generations. For example, when I build PCs, okay, this generation is 15% faster than the previous generation. Maybe I should skip it. But then in 4 or 5 years, when you build a new PC, you often get surprised by the difference you get over the years. And I think this pi calculation really helps us understand the performance improvements, and what you thought was impossible in 2019 can be possible today. So I think that's what I like about doing pi calculations using cloud and other general benchmarks on computers.
Last time you got the record, I noticed that part of the promotion was part of Google Pi Day. You presented it at Google Cloud and Google I/O, and you traveled around the world, kind of presenting this use of GCP. This time around, what are the plans to promote the record this time?
So we did some announcements. We published everything. So my passion is, so last time we learned you can do something very big with a cloud platform, right? And this time I really want to communicate each piece of the technology and techniques. So for example, even digging into the Terraform scripts we used, I think it's worth a 30-minute or 1 hour tech talk, and even talking about tuning the network parameters, like changing the TCP configurations and attaching the threads, setting thread affinities, etc. They are individual topics. So I'm really interested in producing content around actual techniques and technologies you can apply to your workloads. For example, these are the same set of optimizations you'd probably do on web servers, database servers, media encoding, any sort of workloads or any other HPC applications. So my next goal, my next project is use this whole set of configuration and break it in smaller parts and explain what they are and how you can apply to other kinds of workloads. So that's my next project.
That actually leads me on, because I was going to ask, what else aside from this Pi project have you been up to? Because this is obviously the most public thing that you're doing from a more wider media perspective, but your job is more than just this, right?
Right. So yes. So running experiments is one thing. Creating demos, tutorials, or writing tutorials is another thing. Obviously, we have product launches coming up, and I'm working with the product teams to create demos, record videos, and maybe plan podcasts, and so all the outreach. At the same time, some of our jobs is give feedback to internal product teams. So for example, during calculation, because you use the product, you use Google Cloud as an external user rather than internal user, you can see what works well, what could be better, and I wrote a document to give feedback to, so they can make the platform even better. And this is true for other products as well. So I often write, these are called friction logs. So even if things work well, if you find a better way or maybe better perspective, if you believe something should work differently, you can give the specific feedback to the product team. And that's something I also work on. And yes, so there are more exciting new features and products coming up in the future, and I'm working with product teams to make sure we have documentations, tutorials, and sample codes ready for these launches, and that's something I'm working on right now as well.
What made you go down the path of becoming a Google Cloud developer advocate? Because you took the job in 2015. What made you decide that Google was the direction to go in that way?
Sure. There are a couple of reasons. One of them is I had friends working at Google, and they said they were happy working at Google in Tokyo, and so that helped me decide where I wanted to go next. And the particular developer advocate job, I attended a Google event. I think it was in 2011 or 2012. Google Developer Days in Yokohama, Japan, and the topic was about web technologies. But I was really impressed by how the speaker shares the technologies. It was very different from what I knew from industry presentations. It was more engaging, um, fun, and they had demos and samples that I could try at home. And I was like, so this is how you learn about technology. You can change how people learn and get excited about technologies. This is I want to do something like this. And also I like traveling, and as a developer
Yeah.
advocate, meeting people at conferences and learning, and also learning what people do with cloud is another piece of work. So I thought developer relations and developer advocate would be a really interesting job to me. And for this particular cloud, instead of like web, anything, well, I think web could work for me as well. I really like computer architecture and making computers faster. Obviously, I DIY all my desktop computers, and I've been doing this for more than a decade. And
Mm.
I I follow all the hardware news and get excited whenever a new generation of hardware comes out, and dedicating myself to optimizing and making working on a platform is exactly fits in exactly in my interest area. So this is about computer architecture. This is about making computers work and making computers more efficient, faster. And this is something I'm passionate about. So all the factors led to this specific point.
You sound so enthusiastic. I'm never going to get that record, am I? You're just going to keep pushing it and pushing it and pushing it. Thank you so much, Emma, for coming on the channel. Like I say, I've been following you for a couple of years, and I know we've exchanged the odd tweet here and there. But it's great to finally get to talk to you, and congratulations with your new record.
Thank you so much for having me. I really wanted to talk to you and talk about hardware and technology, and I'm really looking forward to continue this conversation in the future.